Okay, so now we're going to look at what conditions are necessary for a market to be efficient overall. And we're going to look at three specific types of efficiency. And when all three specific types of these efficiencies hold, then the market is efficient. So we're going to consider exchange efficiency, which is when the allocation of goods across consumers is Pareto efficient. That's when there's no trades between consumers that could lead one person to be better off, or at least one person better off, and no one worse off. If you have such an allocation where there is no such trade, then you have exchange efficiency. Input efficiency is when the allocations of inputs across manufacturers are allocated in an efficient way. It would fail, for example, if that trade of labor for capital between those two firms resulted in one or both firms producing more of whatever it produces and neither firm producing less of what it produces, then we would say that the initial allocation of inputs was not input efficient. And the last type of efficiency relates to which types of goods we're choosing to produce. So it might be true that we have input efficiency, but maybe what we'd like to do is we'd want to take both labor and capital away from some firm, causing that firm to produce less, and move that labor and capital to another firm, allowing that firm to produce more. If we can find a way to do that, that results in more of one good being produced, less of another being produced, in a way that when distributed to consumers, made all consumers at least as well off, so some better and no one worse off, then the initial choice of which goods to make was not output efficient. So let's start by looking at exchange efficiency. Okay? So we're going to look for allocations which are exchange efficient, which there's no trade that would make someone better off and no one worse off. If we look at this graphically, maybe we can get a better idea of how we could try and find efficient allocations. Okay. And to do that, we're going to use a graph called the Edgeworth Box, or Edgeworth Box Diagram. And what we want to do is we want to look at two different consumers in the market, each of which is getting some number of each of the two goods in this market. Okay? So let's revisit what we looked at earlier in this class when we looked at indifference curves. Remember, we had these indifference curve graphs or maps where we plotted for a given individual the amount of one of the goods that they have versus the amount of the other good that they have. So in this graph here, we have the number of pancakes that Elaine has and the number of bowls of cereal. The further you move to the right along this graph, it implies that Elaine is getting more bowls of cereal. And the further you move up on this graph, it implies that Elaine is getting more pancakes. And then the next thing we did is we plotted all of the different combinations of the two goods that left Elaine with the same level of utility. That's all the combinations of the two goods that Elaine was indifferent between. Now, on this graph on the right, we have the analogous indifference curve graph for Jerry. Again, as you move up this graph, it involves more pancakes for Jerry, and as you move right along this graph, it involves more bowls of cereal for Jerry. Now, what we'd like to do is we'd like to combine these graphs in some meaningful way. So you might think that maybe let's just superimpose them if you put Jerry's right over Elaine's. But there's a problem with that. As you move sort of up and to the right, if they're superimposed, it implies that Elaine and Jerry both get more of both goods. But when we're looking at exchange efficiency, we want to somehow account for scarcity in the market. That if Elaine is getting more of one good, then Jerry is necessarily getting less of that good, and vice versa. Okay? So we'd like to combine these graphs in some meaningful way. We can't superimpose them. What we do instead is we're going to take one of them, in this case Jerry's, and we're going to flip and rotate it. Okay, so let me show you that again. we're going to flip and rotate it. Now we have a combined graph, where as you move sort of up, if you choose a point that's further vertically up along this graph, it implies more pancakes for Elaine and less pancakes for Jerry. Likewise, as you move horizontally right along this graph, it involves more bowls of cereal for Elaine and less for Jerry. Let's look at a particular example here. Let's start at point A. To get the number of pancakes for Elaine, we're going to look at the left vertical axis. So it implies that Elaine is getting 6 pancakes. And to get the number of bowls of cereal that Elaine is getting, we're going to go to the bottom horizontal axis. So point A implies that Elaine is getting 6 pancakes and 3 bowls of cereal. We might also want to know how many of each of those goods are allocated to Jerry at this allocation A. And to figure out how many of each good that Jerry gets, we're going to trace this point out to the other axis. If you were to go up to this top horizontal axis, that would tell us how many bowls of cereal Jerry is getting with that allocation A. Okay, so a given point just tells us how we're allocating these goods in existence across these two individuals. If we move from allocation A to allocation B, you can see that the number of pancakes each of them has remains the same. But as we move from A to B, Jerry is getting 1 less bowl of cereal, and Elaine is getting 1 more bowl of cereal. Okay, so the key point here is a given point on this graph represents the allocation of both goods to both individuals. So let's look at this graph here. Here we have Elaine's indifference curve shown with the red curves. Okay? The ones further up and to the right for Elaine imply that Elaine has more of the goods, and so she is happier. For Jerry, it's the opposite. His indifference curves are shown by these blue curves. And for Jerry, as he moves sort of down and to the left along this graph, that implies that more of the goods are allocated to Jerry. Right? You can see that just by looking at the two axes. As you move down and to the left, it implies more pancakes and more bowls of cereal for Jerry. So the indifference curves for Jerry that are further down and to the left actually correspond to higher levels of utility for Jerry. Now let's look at point A on this graph. It falls on this indifference curve for Jerry, UJ3 for Jerry, and this indifference curve for Elaine, UE3 for Elaine. Now the question is whether this allocation A is exchange efficient. Now we can see that it is not. So let's sort of trace this indifference curve for Elaine down here. We know that point A has the same utility as every point on the indifference curve. So let's look at this point where the mouse is positioned right now. Point C, relative to where the mouse is positioned on this indifference curve, involves Elaine getting more of both of the goods. And by the more is better assumption, it implies that point C is preferred to this point, represented by the mouse, which yields the same utility as point A. Hence, for Elaine, allocation C is preferred to allocation A. Okay. Now let's look at Jerry. Remember, for Jerry, points further down and to the left as he moves from this direction correspond to him getting more of both goods. Allocation A is on the same indifference curve as where the mouse is positioned now for Jerry. So that means that Jerry's utility is the same at point A and at where this mouse is positioned. But point C, relative to where this mouse is positioned, is further down and to the left, implying that relative to this point, point C is giving more of both goods to Jerry. So point C must be preferred for Jerry over this point where the mouse is positioned now, which has the same utility as point A. Hence, for Jerry, point C must be preferred to point A. So we can see that changing from allocation A to allocation C is a Pareto improvement. That is, it is a change in allocations that makes at least one of the two people better off without making either of them worse off. In fact, in this example, changing to allocation C makes both of the two people in this market better off. Okay, so let's think about this. When would you have a scenario in any given allocation where there's some other allocation that would make both of them, or at least one of them, happier? Well, we can see that there's this area that falls below the indifference curve that that point A passes through for Jerry, and above the indifference curve that passes through point A for Elaine. So you're going to have this region that's sort of preferred by Elaine up and to the right of the indifference curve for Elaine, and preferred by Jerry down to the left of this indifference curve for Jerry, whenever the indifference curves cross. So whenever there's a shaded region here. And so when would it be exchange efficient? Well, if you had a point where they don't cross, well, if they're both sort of have the shapes that's depicted here, when are they not going to cross? It's when that point is a point of tangency between Elaine's indifference curve and Jerry's indifference curve, where they touch and have exactly the same slope at that point. Now remember that the slope of the indifference curve was the marginal rate of substitution. It was the rate at which Elaine is happy to trade off one of the goods for the other. Okay? So you have exchange efficiency when you have an allocation where the indifference curves have the same slope at that point and are just tangent, which means that the marginal rate of substitution for Elaine is exactly the same as the marginal rate of substitution for Jerry. Now let me ask you this question. So again, I'm going to do this pause the video thing. So after I ask the question, I'm going to ask you to pause it, think about it, and then when you're done thinking about it, unpause the video. The question is, which of the points are exchange efficient according to this Edgeworth box diagram? Point A, point C, point B, or point D? And remember that you can answer more than one answer. Okay, you're back. Okay, so let's go through this point by point. Okay? For point A, we can see that there's sort of points up and to the right of the indifference curve for Elaine, and they're down to the left for the indifference curve for Jerry. So point A was not an efficient allocation initially. Let's look at point B. Well, this seems to be a point of tangency between Elaine's indifference curve here and Jerry's here. So I would say point B is an initial allocation that is exchange efficient. Now let's look at point C. For point C, we're just not given enough information to determine whether it is exchange efficient. We don't know what the indifference curves look like through this point because they were not shown. Since there's not enough information, I would say we should not answer point C. And lastly, point D, you can see, is another point that falls on Jerry's indifference curve and Elaine's indifference curve at a point where they're tangent to each other, where Elaine and Jerry have the same marginal rate of substitution. So I would say point D is exchange efficient. Now, what does this show you here? It shows you that both B and D are exchange efficient. We have multiple allocations that are exchange efficient. And in fact, if the goods are infinitely divisible, then there's an infinite number of allocations that are exchange efficient. Okay? Some of the points on this, what's called the consumption contract curve, which connects all the efficient allocations, some of them involve Elaine having very little of both goods and Jerry having a lot of both goods. Other points involve Elaine having a lot of both goods and Jerry having very little of both goods. Some points are sort of more evenly distributed. Actually, this point right here where Elaine has no pancakes and no bowls of cereal is also a point on the consumption contract curve, another point that is exchange efficient. So that the point is here, there's a lot of different exchange efficient outcomes, including those where Elaine gets nothing and is starving. So that is efficient, which really highlights the fact that efficiency does not necessarily serve as an argument that's saying this is the best allocation of these goods. Okay? But what we know is if you start at some point, let's say where the mouse is over here, it is not on a point on the consumption contract curve. It is not an efficient allocation, which means that there must be some other point that is on the consumption contract curve that is preferred by at least one of the consumers, and maybe both, and doesn't make either of the consumers worse off. And so that would be a point which is clearly better than where we started out. So we can think about it, at a minimum, we want exchange efficiency, but it doesn't necessarily imply that we've reached sort of the best outcome. But we know there is something better if we do not have exchange efficiency. That is something we can all agree on. Okay, so what's actually really neat about this is that prices facilitate efficient trade in a free market. So if you think back to the earlier lecture on utility and consumer choices, you might recall that the optimal consumption basket for a consumer, given their budget constraint, that is the choice of how much of each of the goods that they want to consume to maximize their utility, is the basket that spends all of their income and sets the marginal rate of substitution equal to the ratio of prices. Now, if both consumers do that, it means that both of them are going to have a marginal rate of substitution that's equal to the price ratio, which means that the marginal rate of substitution for each consumer in the market should be the same as the marginal rate of substitution for every other consumer in the market. Okay, so that suggests that prices should facilitate exchange efficiency. Now you might ask, well, what happens if there's excess demand for one of the goods? Maybe the amount demanded, if you add up the demand for each individual, exceeds the amount of that good that has been produced. Well, then there'll be sort of a scrambling of these different consumers to try and get it. They'll offer a little bit more, and this bidding up of the price of, let's say, good X will continue to happen until the market exactly clears, until the amount demanded is exactly equal to the number of those goods that exist in the market. Okay, so prices will adjust until we reach the scenario where we have exchange efficiency. That's what we sort of expect to happen in a free market, which is a really nice feature.